Good morning. Welcome to lecture 26 on thermodynamics of materials. We are discussing Kirchoff's equation. So, which we got this Kirchoff's equation. We call delta H T2 is delta H T1 plus delta Cp dt T1. We have discussed this. Okay. Now modified form, modified or extended form of Kirchoff's equation. What is this? Consider an example. Consider the following example, then you will understand. The following example. Suppose I actually ask you, this is given to you. Pb solid, this example, reaction is Pb solid plus half O2 gas goes to lead oxide PbO solid. Suppose I give you, it's okay, problem. So this is the suppose delta H 298 is given. Known means given. To find delta H or delta H0, maybe you can write delta H0 1000 Kelvin. So you can proceed this way. Then what is the reaction? This is the relevant reaction is you can write yourself what is this. Oh, by the way, this is actually 298. This is a formation reaction, remember. This is a formation reaction. Here is Pb solid, Pb liquid plus half O2 gas is lead oxide solid. Why this? Because melting point 1000 degree Kelvin is above the melting point. So what is the melting point is what? Note 1000 Kelvin is greater than melting point of lead, T melting lead. What is that value? 600 Kelvin. 600 Kelvin. 327 degrees centigrade is the melting point of lead, low melting metal. Then that is in turn is greater than 298 Kelvin. So what is the trouble? Trouble is for moving 298 to 1000 Kelvin, you have passed through a phase transformation, melting of the solid. So it was solid, but it is liquid here. So how to modify the Kirchoff's equation? It is again from one temperature to another temperature. So I am writing for you delta H0 1000. You proceed in the same way. This is given, so use this. Okay, this plus, okay. So tell me same way, delta H0 298. Okay, plus tell me what? Delta, you can write here PbO. This is actually formation reaction, you understand? So it will be PbO actually. This is also right here. You can write this delta H0 298 PbO means formation. It may not be formation for any reaction, but here it is a formation reaction. So delta H0 298 plus delta Cp dt. As you have already seen, T1 is what? 298. What temperature right here? Question is on 1000 Kelvin. So directly you cannot write, you should not write 1000 because you should go up to the melting point. So first step is go to the melting point, 600. Okay, okay, 298 Kelvin to 600 Kelvin. Then what happens? Then let the melting occur. Let the melting occur. So this is actually delta H melting. There is enthalpy of melting. This is called enthalpy of what temperature? This is 600 Kelvin is the melting point. So enthalpy of melting or which you call latent heat of fusion. Enthalpy of melting, which you in high school use, that is latent heat of fusion. But I use the term enthalpy. Latent heat of fusion of lead, solid lead. This is minus for some reasons. Actually, I will explain you. This is then plus, then melting is over, then again take up from melting. It has been liquid now. So now it take up 600 to 1000. Okay, and delta Cp. But this delta Cp will be slightly modified delta Cp because liquid is no more lead solid. So lead liquid. I will explain this delta Cp dt to 1000. Okay, note. This is the noting. What I have written here? Why 1000 is coming here? I don't remember what is 1000, but this is the 1000. This is the answer. This you can box this. This is your answer to this question that I started. Sorry. This is taking your time actually, nothing else. So you have to look for this. Now here why the minus? Remember when the melting takes place, note this, why minus? Note here. Okay, before this let me correct some points. Note. These 2 points. First of all, delta Cp is what? Tell me. Last day I told you what is the delta Cp? Cp of product minus Cp of reactants. Always remember this. Cp products minus sigma Cp reactants. Remember this. So you do this, apply. What is the product? First one, delta Cp. Cp of lead oxide. Remember solid liquid you have to distinguish. Minus, what is the reactants? Cp lead solid, first one. Until it is molten. So Cp Cp lead solid plus half Cp. Okay, space is a great problem. Half Cp O2 gas. This is the delta Cp. Product minus reactant. Your product Cp. Here half Cp because half moles. So this is delta. But what is the delta Cp prime? I am writing this side to be more comfortable. Delta Cp prime. Can you tell me similarly? See, it has been molten here. This is molten. Then it is lead liquid. It has been lead liquid plus half O2 goes to lead oxide. So similarly, tell me Cp lead oxide solid minus Cp lead what? After melting it has been molten, lead plus half Cp O2 and that's it. 2 things here I have clarified. Another thing I will clarify. What I will clarify? What is the next thing? Delta Cp prime. What else? Oh yes, minus. This is minus. Why minus? Delta H Pv melting is given a negative sign. Is with a negative sign. Because the phase transformation occurs on the reactant. Phase change occurs on the reactant side. This can be easily proved reactant side. That means what does it mean? When is with a negative sign, when delta Hm will be positive? When start. When delta HM, and when the transformation, when the phase change occurs on the product side, for example, lead oxide will be molten. Lead oxide will melt above the melting point of lead oxide, obviously. If we consider the temperature above melting point of lead oxide, then lead oxide will be molten. Okay, so will be liquid, will be okay, liquid. So when the phase change occurs, this is the rule. When the phase change occurs on the product side, say lead oxide, then what we will have? Then we will consider, tell me case, it is not no more minus, because product is not. So then product is moving. Product is solid, then product is molten. So it is plus. And here actually going back. Lead oxide is back. So the negative will come. You may actually we will have some experience, and then we will consider minus. Plus, I'm very sorry. Plus, tell me delta HM, M for melting, remember, M for melting, PbO. That's it. Enthalpy of melting, latent heat of melting of lead oxide. Okay, this is the thing that I wanted to tell you. Okay, so next topic rather, adiabatic flame temperature. Adiabatic flame temperature. Next topic, right? Next topic. Still in thermochemistry. We are still in thermochemistry. Next topic, adiabatic flame temperature, in short, AFT. Okay, this is AFT. The knowledge of AFT, the knowledge of AFT of the adiabatic flame temperature is required in fuel combustion reactions. And it is applied, and this value, and it is applied where? In fuel fire furnace. Combustion I am talking, combustion. You are reading perhaps simultaneously, fuel combustion. And it is applied in fuel fire furnace. What is the example is, e.g. blast furnace itself. E.g. blast furnace. Another is open hearth furnace. Open hearth furnace is fuel fire, but this is open hearth furnace. In short, OH, okay, blast furnace BF, okay, short BF. So etc. There. So we'll use this, okay, fuel fire furnace and this. So this is your status, okay. This is actually this. Now what is this combustion? Next is combustion. What is combustion? Okay, it is fuel combustion reaction or combustion. Fuel plus oxidant goes to products. Fuel plus oxidant goes to product. Okay. So what is fuel example? Example of fuel is fuel. First, what comes to our mind? Carbon. Carbon is a very good fuel. Carbon means carbon solid. Okay, carbon. Then hydrogen is another. Then CO gas, carbon monoxide. Then what else? Say CH4, methane, and many other hydrocarbons. These are the fuel. Plus oxidant is the product. This is called combustion reaction. Okay, at a given temperature and pressure. Okay. Now what is next question is, what is heat of combustion? Next What is heat of combustion? Remember I told you heat of reaction, three types: heat of or enthalpy of combustion. Heat or enthalpy. Heat of combustion. Next, define heat of combustion. I said three types of heat of reactions. One is heat of formation. Next is heat of combustion now, and then still another is heat of solution. In solution thermodynamics we will study. So heat of combustion. What is this? The enthalpy change. Heat or enthalpy. Right here, enthalpy. I prefer the term enthalpy, but popular is heat. The enthalpy change. Remember, enthalpy and heat is same under constant pressure. So enthalpy change associated. Definition. This is definition. So just not qualitative description. Enthalpy change associated with the formation. Can I remove this now? This I can remove. The formation of with the I'm very sorry with the combustion. This is not formation reaction, with the combustion. Combustion means, you know what is combustion reaction? Fuel plus oxidant. Okay, with the combustion of 1 mole of fuel with not any oxidant. By definition, it is not any oxidant. It is oxygen directly, not air. Neither N2O, etc. No other oxidant, not carbon dioxide, etc. So with one mole of fuel with oxygen. Oxygen, as you are aware, all heat of combustion, heat of reaction are at a given temperature and pressure at the end. At a given temperature and pressure. The given temperature and pressure. Okay, T and P temperature. At a given temperature, T and P. Okay, this is the temperature at a given temperature and pressure. Okay, this is, for example, e.g., what is this? I am taking some examples quickly. First I am writing, say carbon. All right, combustion reaction examples: C plus solid plus O2 gas goes to CO2 gas. This is a combustion reaction, correct? Because I have considered the enthalpy change of this reaction will be heat of combustion or enthalpy of combustion. Then another is, okay, C at hydrogen is another gas. The gas form, this is solid coal, coke. Okay, pure, it should be pure carbon, but coke is okay, close to pure carbon. So hydrogen gas plus half O2 gas goes to H2O gas. Examples. Still another is CO gas itself. CO is a good. I have already given some CO gas plus half O2 gas quickly is CO2 gas, and another one I give you now, CH4 gas. Methane can be a fuel. CH4 gas plus oxygen gas. CH4 plus oxygen gas is what? CO plus CH4 plus O2 is CO2. I am very sorry. CO2 plus 2H2O, right? Gas. These are gas. So this you have careful. This are that. Now I take up the next is exactly the term adiabatic flame temperature is what? For 2O2. Thank you very much. See, 1 mole, have you noted? These are fuels, all 1 mole. Okay, these are all fuel 1 mole, right here. These are all fuels. How many have considered? 1 mole. Okay. Next is adiabatic flame temperature. Okay, again back to determine the adiabatic flame temperature, AFT, flame temperature, AFT. The reaction mass adiabatic, you know what is this? Adiabatic no heat transfer, no heat interaction. So here actually the adiabatic flame temperature, the reaction must be carried out in such a way that no heat is lost, that no heat is lost. This is your okay, very good, very good. Achha, by the way, examples I gave here, what I'm missing here, one more correct. Another thing is at a given temperature, pressure. So you add this THP, etc. Constant temperature, pressure. So this is, so that is also adiabatic. No heat transfer, exchange between system and surrounding. See how we are carrying out interesting. It's an interesting way of carrying out an adiabatic process. It is not insulation, no insulation, still adiabatic. You consider this reaction, consider the reaction. Consider the reaction. What is the reaction? The fuel. Adiabatic flame temperature is CH4. CH4, that particular reaction I take up again 2O2 gas. This is our study. We understand the adiabatic flame temperature in the light of this reaction. This is what I am writing something, you follow me. CO2 gas plus 2H2 gas. I think I should do one thing, that is these are not anymore required. This is what I write here. Adiabatic, this condition will maintain, and constant pressure. Constant, P means constant pressure. These two conditions will maintain for this reaction. Okay, remember this. So how to carry out this, I will show you. You have seen Bunsen burner, high school, very good, very good, very good. Or the domestic stove will do also. So I am doing what? I am carrying out this reaction. You follow me. There are two channels in Bunsen burner. Two channels. One is the fuel, and another is the oxygen, means air, oxygen. These are two channelized. Okay. So it is say 1 atmosphere. Okay. 1 atmosphere. I am entering this oxygen also. I am entering 1 atmosphere. Both 1. Now they mix up here with 1. You know, 1 atmosphere, 2 gases mix up, become 1 atmosphere. Okay. They does not become 2 atmosphere. Okay. Both when you mix actually, this is constant pressure. So one, and then you light the flame, light the gas, burn the gas quickly. With a match, strike a match and strike a flame here. Light it. Gas is issuing and light. Then it bursts into a flame. Burst into a flame. This is the flame. Okay. The flame will. This is the flame. Flame contains what? Flame. Okay. So CH4 plus O2. This is the input. Inlet. This is the exit. Exit gas. Inlet gas. Achha, by the way, I made a mistake here. I should correct this. What is this? They are hot temperature 298 K. Please note this. I am very sorry. At temperature pressure I mentioned. And what is this? I tell you, hot temperature, obviously the flame temperature. The exit gas at a T flame and 1 atmosphere. This is the overall reaction. I have written overall, consider the overall, consider the reaction is overall reaction. Overall reaction. That's it. So this is the flame. At a plus, you may say, sir, what comes out, this is the product. But some unreacted gas, maybe, okay? Small, a negligible amount plus a negligible amount of unreacted gas. Why negligible? This is a too deep a topic. Amount of unreacted gas. So this is negligible because, why this is negligible? Why negligible? There is some science, deep science here, negligible. Because equilibrium constant is something that you will study later after the second law. Equilibrium constant for this reaction is very high. Means very high means almost full conversion into product. Almost full conversion into product. So unreacted very small. Because why negligible? This you will not understand at this stage, but you should know that because the equilibrium constant of the reaction is large. Equilibrium constant of fuel oxidation. Constant of what is your name? 3 minutes outside. Equilibrium constant of a fuel oxidation reaction is typically very large. Is typically very large. If it is very large, means it leaves very small amount of unreacted. That is full conversion. That means that is the reaction tends to be goes almost to full conversion. Almost to full conversion. Full conversion, you know what is the meaning of the full conversion? Is that almost fully converted into the product. So no unreacted. This is the meaning of full conversion. This you will understand later. Second law. Reference. The second law, then you will understand that you will learn more, know more about it. The second equilibrium constant is the second law. So I will consider this. Okay. So this contains what? This contains this gas. What is burning? Gas is burning. Okay. So CO2 plus 2H2. You write this T frame. Okay. At the T frame and 1 atmosphere. So these I have written. Okay. Alternatively, give a picture here. Right here. Give a picture here. Alternatively, you write this. You show this. Alternatively, how you do this? Your standard figure is what? Alternatively, this is running out. Let me draw this quickly. You tell me what will do this? I'm drawing short. Start constant pressure. Constant pressure and okay. By the way, how salt is adiabatic? Interesting question. This is exothermic reaction. Did I say this fuel combustion exothermic reaction? Okay, fuel combustion is an note. Fuel combustion is an exothermic reaction. Note here. Fuel combustions is an exothermic reaction. Or combustion is an exothermic reaction. Means delta H is negative. Last I told you, exo means Q negative. Q is delta H under constant pressure. So delta H is negative. Okay. So I tell you before it is too late today that in this context recall. Remove this. Remove this. First I'll go to that star before this. Star. I'll give it deeper. I use this star. Note in this connection. Important, very useful information or knowledge in this connection. All combination reactions are exothermic. Very easy. That almost rare. I came across about 1, 2, 3, 4, etc. Millions, okay, trillions are this follow. This means what is the in this connection? All combination reactions are almost all. Let me almost I say almost all. Right first initially. All combination reactions are one or two stray exceptions. Don't worry. All combination reactions are exothermic. Exothermic means write in bracket delta H is negative. This is one. Good, very good, sir. Then what else? Then all dissociation reaction. Opposite of combination is what? Dissociation. Dissociation reactions are endothermic. Obviously, the opposite means will be opposite, in opposite direction. This is opposite. Example, okay. Example here, continue. Example, metal solid, easiest. All combination, not only combustion. Come in, get it. M solid plus O2 gas is MO2. If I ask you what is this, what about its sign in delta H? What will be your answer? Delta H is enthalpy change, negative. Delta H is negative. So write, okay, I don't have much space crunch, so let me write short delta H is forever. Remember this principle, very useful. And opposite is what? You said the opposite is, tell me what is that?
It is combination and opposite.
So what shall I write? Shall I write opposite is dissociation? Answer to the point. See, what is one asking? So the opposite is opposite, MO2. Don't repeat what I have said there. I am asking something, apply that. Goes to M solid plus O2, which is dissociation. Delta H is positive. Okay, happy? Now, another important question. I am coming to the alternative figures. This I'm coming to this. Next is, why it is adiabatic? How it is here? Okay, I have given star to there. Okay. Now this, a double star. Okay. Why? Here itself. Why? Double star. Why the reaction is adiabatic? How is the reaction adiabatic? How adiabatic gas must react insulation, etc. What you are doing here? You open surrounding system, gas reaction system. This is reaction system. Free. Adiabatic means actually, mathematically adiabatic means Q is 0. Insulation or whatever, that is actually the common practice of attaining Q is 0. Heat interaction must be 0 between. But this is what here actually there is scope of heat interaction. See, heat will dissipate to the surrounding, but fast. The moment you strike the fire, right, then that moment this attains that temperature. So there is not enough time to dissipate into the surrounding. You might say, but it is burning for a while, for say 10 minutes, 15 minutes, 1 hour, 2 hours. So then, no, each stream, fast. No loss. Quickly converting to high temperature flame. Then and escapes. Okay. Then again next stream coming. The same thing happening. Fast. Really fast. So this is always high temperature. Okay. Of course you cannot avoid some loss. Okay. There is loss. Okay. Loss of heat to the cooler surrounding, but that is negligible because it is very fast, not slow, not getting enough time. If you don't allow enough time to dissipate the heat, it is adiabatic. Principle is Q is 0. You have made it 0. So fast you have carried out a process, it doesn't get time to dissipate the heat. That is possible. Time given it will. Then it is non-adiabatic. This is the principle. Okay. So how the reaction is adiabatic? Answer. The reaction occurs so fast, the reaction or flame production, leading to flame production, the reaction leading to flame production, flame production is so fast, this is the underline, is so fast, not enough time to dissipate. So there is not enough time to dissipate I'm trying hard to dissipate heat. Okay, to dissipate heat. Write this, right? Keep on writing. Heat to the surroundings. Your language use to the surroundings. Hence, to the surroundings. I cannot remove this figure. Okay, to the surrounding. That is Heat interaction between system and surrounding is 0. Okay, that is no heat loss. So that is the reaction is adiabatic in nature. That is the reaction is adiabatic. No heat loss to surrounding. That is the adiabatic criterion. This is a new way of getting adiabatic. So the reaction is adiabatic in nature. 10 minutes outside in nature. So this is happening. So this starts. Now alternatively, how will you do constant pressure adiabatic? How will you do this? Yes, I start. This is state 1. Call it state 1. Constant pressure adiabatic to be adiabatic. Insulation. So what you have taken? Tell me. Tell me CH4. Initial state CH4 and O2 means 2 O2. You can write 2 O2 if you are interested. 2 1 atmosphere. Okay, 1 atmosphere. This is also 1 atmosphere. This moves into what? Tell me. This constant pressure still is 1 atmosphere. Inside will change. Inside has changed to and still adiabatic. Right here. Insulation, right? Adiabatic. Insulation. Adiabatic. Right? Adiabatic or insulation. Okay. Insulated. Insulated means adiabatic. Insulated. Sorry, you understand this. Unnecessary I am writing. Time is wasting. CO2, 2H2. What temperature it is? What pressure? Is 1 atmosphere. Still 1 atmosphere. Oh, I am giving the 1 atmosphere. But what temperature? Oh, temperature is 298. I have not written here. That is very bad. That I should have written. Right? 298 Kelvin. Initial state. 298 Kelvin. After reaction, heat actually has not. Let's see. Follow here. This is better for you. This is deeper. This is easy because it is insulated, so no problem. Heat is here. Heat goes where? Nowhere. So where it remains? Inside. And heat up the contents. And that it does. That is the adiabatic. It will heat up the contents. Okay? And who are the contents? The products. What temperature? T flame. Okay? See, 1 atmosphere I have given here. T flame. Happy? So this is the whole status. Okay? Now solve the problem. So okay, so next is we will actually get how to find the flame temperature. Okay, how to find the flame temperature quickly. Break up. So I have to follow this. I am removing this. Now this is actually call this equation 1. Okay, I am writing. I don't have much time. Okay, so call this. So I am cancelling this. This is reaction 1. Okay, now I see giving. I am writing something. Now, follow me. Delta H1. Label. You have to label the reactions. Otherwise, you have to write that reaction. Oh, again, I repeat the reaction. No. Same time. 1. Delta H1 is what? I am writing. You follow. Is Q, sir. I am writing with logic. Follow the overall. See the overall. Delta. This is the reaction. But reaction has a strange feature. What is the feature? Not usual. What is? Sir, one side is 298, another is another temperature. Very high temperature indeed. It's 1500 Kelvin. So it is different type. So if we want to handle this type of situation, we have to break it up. So break it up. Before breaking up, I am showing. I will break up soon. Okay. Delta H1 is Q. This is correct. Why it is correct? This is correct because constant pressure. Constant pressure gives this. Then I am writing 0. Why I am writing 0?
Because adiabatic.
So when these two are, remember, adiabatic is a very common consideration. Isothermal adiabatic, but adiabatic, you should be careful. So delta is 2 Q, Q to 0. Constant pressure adiabatic combination with this. So delta H1 for this reaction is 0. Now we'll use this. We'll use this. Please, let me give the breakup. Shall I write the breakup where? I think these are unnecessary. All unnecessary. Is okay. All unnecessary. All a negligible amount of it. I am just removing this. I am using it as in short 1. Okay. Remove this. Why negligible? All answered. Remove all. All? Okay, oh, sorry. May 22, May 22, 2023. Okay, start. Breakup. So with the help of breakup, we will handle this problem. Breakup of 1, reaction 1. This is needed, this is needed. You will solve the problem sheet, assignment, always breaking up. Next day I will start. Tomorrow in fact I will start solving. 1, 2 at least you try to get solved. Okay, 1, 2 and read the problem 4. 4, 5 try as much, but 1, 2 is very easy. Maybe high school also to some extent. Breakup of reaction is 1 is what? I'm writing. I'm breaking up. See, follow with me, the breaking up of this quickly. I'm writing this CH4. I'm writing this step 1, step, right, step. Okay, 1, CH4 plus 2O2 goes to CO2 plus 2H2O. Same temperature. What is the temperature? 298 Kelvin. I don't change the temperature. Product changed. Okay, reaction has occurred 298. And if you ask your 1 atmosphere, say at this 1 atmosphere or any pressure, it's not so important though, because enthalpy is not so strong function of pressure, but don't worry. That means what does it mean? What does it mean? 298, 298. You can write that also. 298, 298, 298, 298. A state must be properly defined. So I have written here just the commonness. So 298. So in case you are interested, so that is also 298. 298. If you insert 298, instead of writing so many times, you may write on the top. Okay. Then second step is what? Second step, write this. Second step here. Okay, since I actually then these two gentlemen, CO2 plus 2H2O, right? Nicely, 298 Kelvin. See, it is 298 Kelvin, CO2 plus, right? And this product goes to the final. What is the final? Tell me. T flame, right? T flame. Okay. This is actually T flame, and this is 1 atmosphere. You can write. You are interested. 1 atmosphere. But temperature change. So these are the typical breakup. Typical. Note this. Learn this forever. That this is how. Now, what is the advantage of this breaking up? Easy. Now it is easy, and that's it. That also start. This is alongside. Yeah, here from here. Okay, start. Delta H1. First of all, do this. Delta H1 is what? Delta H1 plus delta H2. Do you agree? You agree. You add this to. They say this start, cancel. This final is initial here. 298, 298. So cancel, and what it leaves? Right hand side is T flame pressures. Okay. So fine. So that is the breaking up. So we actually will add this to, will get back to the overall, which is actually we represent the process. Okay, the adiabatic flame temperature process. So good boy. What is delta H1? Now see on by. Now see. This is what type of reaction? This is what we call this? 1. Sorry. Take a look here, not here. 1. Step 1. What is this? This is merely a 1 temperature and pressure. A reaction is carried out. What is the name of this thing? Is delta H1 is what? Delta H1 is what? Name, any name? Heat of reaction. Anything does not work if you don't have any specialized form. Always general name. Heat of reaction, sir. Heat of formation could be, it could be conversion, but these are all actually under the purview of heat of reaction, sir. So this is heat of reaction. This is a formation reaction, by the way. Suppose you are actually wrong. Is it a formation reaction? Yes. Why it is not? Formation reaction is what? Yes, you're right. Yeah, what you said? CH4. Good. Not constituent elements, sir. The compound left hand side. So who will accept this, sir? This is not formation reaction. Okay. And this you may call this is a, but this is a what type of reaction? Say, give me this. This is a, it is not. What is the, then what type of? Perfect. Why, sir? Why satisfied? 1 mole of the fuel. Fuel is the CH4. And the rest we don't care. And a given temperature, pressure, all set. So combustion. But general name is heat of reaction. Now, how to get delta H1? Tell me. I taught you last day. Now refer to last day's class. How to get this one? Delta H1? What is the way? How to get delta H1? Anything you can write for delta H1? Yes, yes, yes. Summation of H of products minus H of reactant, it is fundamentally true. Basic principle, but don't use this. Very interesting, but don't use this. I actually whisper to you. It will not be used much. Practical. Data, H of this H, this H data, how will you get? Where will you get? Data for H, absolute enthalpy, delta, change. What is in the which form? Which form they are available normally? In books? You will get delta H for this. Unlikely, very unlikely. There are millions and millions of reactions. Who will tabulate them? But there is a trick of tabulating them. So, in 10 pages they will cover. 10, 20 pages? In trillions, if you write, actually it will be 2 million page. Okay, 2000 page for the data only. Tell me what I said. What I said then? What I said? Yes. How you write the delta H1? In terms of, yes, in terms of use of delta H. Delta H of what means? Formations. Formations. Formation is the key word. All formation data are available. You will be giving him a problem. He will ask formation, but don't. Not beyond that, sir. We don't need. Not anything above. Just give me formation. Formation data are generated. Experiment. You experiment. You generate data, and you do yourself also. You should do actually. Generate data for calcium carbonate or some reaction. So delta H1. So formation data are available. So moreover, if it is not available, you will write. Then you will say this data is not available. No, I cannot solve the problem, and perhaps no one will be able to. In terms of formation, delta H1, right? That's shall I write here delta H1 or writing? What is this? Delta, better I write step by step. Delta H1 is what? Right. Formation. Tell me, what is that? Delta H. Tell me. Delta H CO2. Product minus again this way 298. One and also I am not writing. Pressure is not important. Plus 2 delta H formation. H2O. Good boy. H2O 298. Minus reactant. Minus reactant is, tell me. Good boy. This 298 then who is saying? Who told? Minus, he says minus 2H delta H delta. What you will say? I have written up to this. Up to this I have written. Anything else? C says oxygen. Shall I include? Any opinion? No. Palm, no, nothing else. Only for in terms of formation. Whose formation is oxygen? No, it is not a palm thing. It is element. No. Remember, then that I cross-check that if you write this way, you will get back to fundamental. The fundamental one who said, someone said, H of this plus H of this. When it is in terms of H, what you will say? H of this plus H of this minus H of this minus 2H of that. O2. Then include. In terms of H, include. But in terms of formation, don't. You don't have to. You should not. You may not. Okay? Because if you expand this, plus the W. One reaction I showed, CO plus half O2 or something like that. I showed you. Okay? So both actually they are in agreement. In terms of compound, remember forever. When compound, only compounds. This as good as. I tell you, write this as good as I am writing. If you expand this, H of this plus 2H of this minus H of this minus 2H of this. Then the HO2 will be relevant. Don't worry. So these data are given, right? Given. These are given. Given means given data. So this will be This will be known. Is and then and is large negative value. Large negative value. Happy? Delta H2 is what? 2 is what? Large negative. Why? Why negative? This is negative or positive? This is negative or positive? All are negative. This is negative, this is negative, these are all negative. Yes, a formation. All formation by principle is negative. This negative minus this negative, though, still it will be large negative. And what is that is the additional statement, don't worry. Anyway, then delta H2 is quickly. Star. Double star maybe. Here, delta H2, right, this side, Delta H2 quickly. Delta H2, 5 minutes, okay. Delta H2, yes, okay, I'll quit. Delta H2, please tell me, I'll be very happy. Delta H2, yes, someone is saying something. Delta H2 will be what? Okay. Delta H2, follow. Oh, this goes to this. Oh, what are they? CO2 298 to CO2 T flame, 1 by 1. Plus this similarly 298 to T flame, 1 by 1. CO2 goes to one temperature to another temperature. And under obviously the same pressure is not important. So what is this? CPDT? Heating, CPDT, NCPDT. Remember, I am writing here. This is a what type of reaction? So this is actually a mixture. One temperature to another temperature. Follow, always can go, oh, I have to break up because one temperature, another temperature. Oh, then what you did? Same temperature, then the heating. So what is this reaction? This is a chemical reaction breakup. First step is chemical reaction at a given temperature. This is your standard breakup. And what is this? Tell me. Heating. This is a chemical reaction. This is a heating. Chemical reaction, heating. Apply heat of reaction properties. And this is pure heating. I don't write too many things here. So please do this. Delta H2, as you have correctly said. So 1 by 1. That will do. 1 by 1, then combine these two, cover 2, address 2. So Cp, I am writing for you. Cp, CO2. 1 mole Cp, 1 mole CO2, and then what else? Plus 2 mole similarly Cp, H2O. Perhaps you can give a good bracket. Integration, tell me, 298 to T flame. That's right. So tidy up. So this I am writing here for you. So 0, this, remember, first here it is 0, remember, it is 0. Delta H1 here is 0. Okay, so overall is this. So what does it mean? So write this here. So remove all over. So 0 is, let me write, 0 is delta H1 plus delta H2. Delta H1 incidentally is this. Where is the delta H1 here? Delta H1 here and delta H2 here. Okay. So please copy this. Is what? What's the delta? Write that. Write full write. 298. Sorry, it will take time though. Write that. Plus 2 delta H. Acha. This is actually this is okay. 298. Acha, delta H1 I am writing to saving time. This is giving what is delta H1. I am writing delta H1 plus delta H2 is writing once more. So this is, I have shown large negative. What is delta H2? This is delta H2. You write. Okay. This is large negative. So this is okay. Write once more quickly. Cp. This I say plus 2 CpH2. 298 to what? T flame. This remember sometimes in short you might see somewhere this, remove all this, remove all, everything is over. Okay, it is sigma Cp, not delta Cp. Sigma means sum. Sigma Cp, you may say call it products. Follow this. Sigma Cp products. This is adiabatic flame temperature. What product? CO2 is a product. H2 is a product. This is the product. Original reaction CO2 and H2 product. So this is actually this, but you may call sigma Cp products actually, no? Or just you write this. If you don't follow this, right? What is delta C? Sigma Cp? This. What is delta Cp? When you use delta Cp, dt, Kirchoff's equation. Delta Cp. Today. Delta Cp, delta Ht2 is delta Ht1 plus delta Cp. Delta Cp is Cp of product minus reactant for the reaction. And this is what? This is the second step is what? Second step, see here, second step being weighted. See, this plus this, my product, one product, second product, third product, fourth product, sigma Cp products, dt, okay, sigma Cp, okay. I'm writing for it, dt 298 to T. Please follow. This is large negative. That means this is what? This is what? That means this is what? This must be large negative, means this is large?
Positive.
Good boy, good boy. Help me. And if it's large positive, tell me what is the T flame? What is the T flame? Yes? It's large value. Large positive, this one. This must be large. That means T should be accordingly large. For a given Cp, what is Cp? Say Cp gas signal, 30, 28, etc. So only, sorry. What is this? Final, right? T flame. And this leads to T flame. Extraordinarily large is large value. Typically 2500 Kelvin. You all said. I'll stop here. Okay, thank you. I'll take up. Still, it is not over. Almost. I'll help you with one problem that I'll do tomorrow. Okay. But otherwise, it is over. Thermochemistry, first law of thermodynamics, all in a sense over. But I'll take up one small thing. Thank you very much. With these words, we have actually completed today's class. No, thank you very much. Okay. So, hold on.